We're excited to feature the Honey, I Shrunk the Payload challenge on our show. The challenge was made possible by the NASA Tournament Lab, which facilitates the use of crowdsourcing to tackle NASA challenges. The challenge is funded by the Game Changing Development Program in support of NASA's Lunar Surface Innovation Initiative, which champions technologies needed to live and work on the moon. Judging for this competition included representatives from the Space Technology and Science Mission Directorates, as well as engineers from NASA's Jet Propulsion Laboratory. The instrument payloads developed under this challenge could enhance future science missions on small platforms like rovers, helicopters, and CubeSats. Data from these types of crowdsourced miniaturized sensors could enable future robotic missions to protect and improve life on Earth and in space, and to discover the secrets of the universe. Finally, the Center of Excellence for Collaborative Innovation managed the contract with HeroX for the competition and awards under the Prizes, Challenges, and Crowdsourcing program at NASA. Clearly, a lot of effort went into this incredible challenge. And now, on with the show.
Welcome to NASA Edge.
An inside and outside look at all things NASA.
Hey guys, today we're going to do things a little bit differently on set.
I know, the set looks great.
I look great. This is great.
Today we're talking about miniaturized payloads, about HeroX's Honey, I Shrunk the Payload challenge, where teams are shrinking down flight hardware to fit on small robots that NASA is sending back to the moon.
You know, Blair, I really love this idea, and I'm guessing you're going to tell us about a mission to do just that?
Yeah, and I'm guessing it's going to be a super cool idea, Chris, just like all of Blair's ideas.
That's right, Franklin. But to help our audience understand exactly what I'm talking about, I had a chance to sit down with NASA Langley's Mark Thornblum to tell us all about the Honey, I Shrunk the Payload challenge.
Sweet. Hey, let's check it out.
Mark, you work with Game Changing, and not only is that a really cool name, tell us what it is and how you develop these cool technologies for NASA.
Sure. Well, Game Changing is the Game Changing Development Program Office based out of NASA's Space Technology Mission Directorate. And we have about over 100 projects that are at what we would call the mid-technology readiness level. So they're great ideas and great new concepts for how we would have either a new technology or advance a current state-of-the-art that has a future in making and enabling our future missions for NASA, either for NASA science or for NASA exploration. And a lot of our projects right now have a future on lunar exploration and a sustainable presence of humans on the lunar surface.
And that's with Artemis, right?
Right. Most of our projects right now, or at least a good bit of them, are working on what we'd call a technology demonstration in order to prove themselves to be ready to be infused into an Artemis-like mission. So what we do is we start where the projects are now. They're better than just a good idea at this point. They've been shown that they're feasible and that they've shown that they really have a promise to work. So we work with these projects around the country to get them ready, get them packaged, form, function, and then demonstrated either on the lunar surface or on a ground demonstration or maybe a suborbital flight. If they're successful, then our goal is to put them onto a mission and to infuse them, or to infuse them into the commercial market and let these technologies become commercial products that the whole space economy can utilize.
You now have competitions where you're inviting people to participate in this process. Tell me about these competitions that Game Changing's working with.
Right. Well, let me specifically talk about Honey, I Shrunk the Payload, because that's where we want to kind of talk about today. With Honey, I Shrunk the Payload, we are engaging the public. So in this particular competition, we were interested in small instruments. Our platforms for space flight have gotten smaller. The rovers are getting smaller. Even the lunar landers that are developing now for the commercial lunar payload services, those are a little bit smaller in scale than what you might be kind of used to for, like, I'd say, a human landing system or something like that. So with these smaller platforms, you need smaller instruments to put on them just because of their capabilities. And so with Honey, I Shrunk the Payload, we have asked the public to generate ideas, submit their ideas, and really see what they've got and see what's out there. So we get a lot of benefit out of that. We get to see what small instruments are out there, which ones would be useful to advance science and exploration on the lunar surface. And then hopefully we get to actually fly them.
Was there any specific guidance that you gave the participants as they worked at this competition?
Absolutely. So we knew that we wanted to engage the public with this, and we knew that we were going to have to help them. So we worked with our partners at JPL, and we came up with what we would call an interface document. We gave all the participants constraints and parameters for how they needed to design their payload. So first, it has to be a certain size.
Small.
Small. So think bar of soap. So 100 millimeters by 100 millimeters by 50 millimeters. That's the package that you have to fit inside. You have to weigh less than 400 grams. And then on average, you can only consume about 4 watts of power on average. And that's kind of the parameters that we gave them. And then the last thing was your instrument has to do something useful and interesting on the lunar surface, and it has to also be applicable to the types of challenges that NASA is facing for Artemis and for sustained presence on the lunar surface.
And it makes perfect sense, because if you are sending smaller spacecraft, then you will need these smaller instruments.
Right.
And so how do you know when you've been successful at game changing? When do you know that you've actually achieved your goal in delivering this technology?
So in the world of technology development, we have a numerical scale, which we call appropriately the technology readiness level. And it's a scale from 1 to 9, 1 being basically a really good idea on the back of a napkin. Okay, that's, hey, here's a great idea.
Where all minds stop.
Yeah, right. And a lot of good ideas end. But and then all the way to TRL 9, or technology readiness level 9, which means used regularly for a particular mission, available to purchase on the commercial market, and is readily accepted as this is a space flight, instrument, if we're talking TRLs for space flight. And so all of our projects are in that kind of 4 to 6 range, and it can go a little below, it can go a little above, just depending. Typically, our projects end with some type of demonstration, and that can be on the ground, in a lab, that can be on a suborbital rocket flight, it could be on a sounding rocket, it could be on a full LEO mission, it could be on the space station, and in this case, for Honey, I Shrunk the Payload, we're hoping that this will be on the lunar surface demonstrated. So when those demonstrations are done, that typically gives us confidence that from a technology standpoint, that particular technology has the fit, form, and function to be useful and survive in that environment that we're going to put it in. So at that point, we would then look for infusion opportunities. We look for a mission to adopt that technology to use, or we look for a commercial partner to go and develop it further and then commercialize it.
Man, that was probably the best interview we have ever done, Blair. Spot on.
Yeah, very informative. But now I want to know more about Honey, I Shrunk.
Uh-oh.
What? What is it? What are you doing?
I just finished shooting the first segment of our show with these way cool miniaturized versions of ourselves. I mean, look at the accuracy. I mean, I'm depicted perfectly. And you can see the detail. It's so profound.
Now, how did you do all this without using our voices?
Oh, trust me, I got that all worked out.
I don't like the way that you're handling me, Blair. I don't think you should be doing this with toys.
Oh, no, it's acceptable.
Hey, I look pretty good.
Well, I guess I look pretty good as well. Where are we at, Chris?
You're watching NASA Edge.
And inside and outside?
Man, we don't need to do that. I've already done that. I did the first segment. It's already done.
You already interviewed Mark?
Oh, yeah, it was great. He's great.
So what action figure did you use for him?
Actually didn't use action figures, did the actual Mark.
Oh, he was 1-to-1?
Yeah, 1-to-1. Yeah, scale lingo. Yeah, absolutely.
Now, what kind of scale are we talking about? Are we talking about CubeSat small, or are we talking about Saturday morning cartoon shrink ray small?
It's a good point, Franklin, because I love the shrink ray idea, and that's what I thought it would be. But it turns out that they're looking about wallet size, which is kind of CubeSat size, but they're using real science and engineering to bring that technology into this new form factor for the challenge itself.
Chris Small.
Yeah, there you go, right? So I had a chance to talk to the teams about their particular payloads and how they actually managed to get it down to size. Let's check it out. Joining us now are 3 representatives for the finalists competing in the Honey, I Shrunk the Payload Challenge. Those teams are Sun Slicer, Water Snooper, and URAD. Let's talk about URAD first. Christian, can you tell us about your payload, URAD?
Sure. So URAD, or microrad, is intended to be a more compact, lower-cost radiation sensor that will enable future missions to deploy radiation monitoring equipment much more broadly than has been done in the past. So the name was inspired by the radiation assessment detector that was carried on the Curiosity rover, which was used to survey the Martian radiation environment both once the rover got to the planet, but also to assess what the radiation dose would be on the journey to Mars. So sort of following on from that basic concept of being a very generic, broadly applicable radiation sensor that can tell you a lot about different types of particles and measure the energies of those particles, we decided to name our payload MicroRad, reflecting that it has, as much as possible, similar capabilities, but in a much smaller package.
What were the challenges of taking that standard radiation detector and sort of getting it down to that very wallet-esque size payload which you accomplished?
So there were definitely a lot of challenges, both implementation difficulties. For example, the chip shortage really caused us a few issues, but also technically as far as getting the capabilities we wanted in such a small package. But thankfully, we were able to leverage some novel technologies that really only became available in the last couple of years to do that. So that was definitely a challenge. Basically, how many new technologies we were trying to leverage and cram into such a small payload, and also do it with such a small team and on such a short schedule.
Christian, what are some of the broader uses for the technology you've developed for URAD?
So URAD is very unique as far as being very low cost and small size. And it's also not specifically focused to any one type of measurement. So it's very good at characterizing sort of a general radiation environment. And that sort of lends itself to a lot of other applications beyond the immediate needs of NASA or the immediate needs of the Artemis program. Potentially, I could see applications related to national security, for example, assessing whether someone's trying to smuggle radioactive material into a port, for example. But there's also other applications in space. For example, it's small and cheap enough that you could put one on a large number of spacecraft, and then that would give you spatial diversity as far as the radiation measurement, which could be useful for understanding the structure of CMEs, perhaps, or perhaps it could be used for being able to discriminate between hostile anti-satellite action versus natural effects as far as when radiation effects show up on a spacecraft, being able to tell, is someone pointing a particle accelerator up at the satellite, or is that the radiation that's just coming naturally from the sun, for example.
Christian, thanks so much for taking the time to explain URAD. Next, let's talk with Phil, who has Sun Slicer. Phil, can you tell us about Sun Slicer?
Hello, Blair. Yes, Sun Slicer is a miniaturized X-ray spectrometer that's been adapted for the harsh lunar environment, as well as to ride around on a miniaturized lunar rover.
What would you use a spectrometer, X-ray spectrometer for on the lunar surface?
We've tried to keep the instrument as versatile as possible. So there's many different science experiments you can do. The big one is prospecting for the purpose of in situ resource utilization. And we can leverage the sun somewhat as a X-ray or alpha or radioactive source to illuminate the regolith, and then leveraging X-ray spectroscopy, we can see what the rock-forming elements and hopefully their relative abundances in the regolith.
I like that, a lunar prospector of sorts.
Correct. There are also a couple of other applications. For the initial phase of the competition, we came up with a cool science idea that allowed measuring active regions of the sun to very high angular accuracy compared to what you could do with orbital assets. And that experiment was all about lunar rover mounted Sun Slicer pointed at craters on the moon that could shutter or block the sun's X-rays as it rose or fall behind that crater, and then get enough imaging information to map the size of those active regions. And then lastly, for free, you get radiation monitoring ability up into the high X-ray range, which is interested in to keep our astronauts safe when they return to the moon on the Artemis program.
Awesome, thanks so much, Phil, appreciate it. Let's go now to Tibor Pasher, who is actually in Budapest, and he's gonna tell us about Water Snooper. Tibor, what is Water Snooper?
Hi, Blair. Greetings from Budapest. The water snooper is a very small, actually a neutron detector, which is able to look for volatiles, hydrogen and water ice on the moon surface.
How did you accomplish this task in such a small form factor for Honey, I Shrunk the Payload?
The idea is actually from our colleague David. He was thinking of how can we use industrial CMOS sensors to detect neutrons. This looks crazy, but we managed to put just 3 really good quality industrial CMOS sensors in this very small 10 x 10 x 3.4 centimeter box actually, and it looks fine. That works everything. The challenge was actually to put also the electronics into that box, but we managed that as well.
Now, the idea would be that you would put this payload on a rover, correct?
Yeah, that's correct. Actually, so if we manage to put the snooper on a rover, then we can just go around and look specifically water if we know that the area is a potential area for water ice or hydrogen. On the other side, we can make a kind of prospecting map, looking at what is there actually, where it would be useful to dig for water ice. So the snooper is able to look about 1 meter into the regolith, and this is the upper region of the regolith where we expect to have water ice. And if we know how much is there, how much water equivalent hydrogen is there, then it might be a good chance for somebody to follow up, dig it up and make water and then hydrogen and oxygen from the water ice.
That's awesome. Tibor, thanks so much to you and your team. And I want to thank everybody who joined us today, all the participants for Honey, I Shrunk the Payload. We wish you all the best of luck and hope to see you all fly these payloads to the moon. Thanks, guys.
Thank you so much.
What really impressed me about these teams, guys, is the fact that they've taken technology and miniaturized it, basically shrunk it down for the challenge, but all the things they're looking at are all things that NASA needs to accomplish for us to develop a sustainable presence on the moon in Artemis.
That's a great point. NASA's not going to be able to do it alone. We're going to need, commercial industry, academia, other government institutions, the international community, and the general public. And this is a great way to get the general public involved and excited about the Artemis mission.
Yeah, and crowdsourcing the development of flight hardware is just brilliant, and this will be the first time that it will be done.
Not only that, but this technique will be used in other challenges to come down the road.
Yeah, and the payload interface requirements were developed by JPL, and all the teams had to submit their payloads to them for testing. My next interview had a lot to do with that. Let's check it out. I'm here with Josh Ravage, who is a mechanical engineer at the Jet Propulsion Laboratory, and he was part of a team who received the Honey, I Shrunk the Payload payloads to test their flight worthiness. Joshua, can you tell us a little bit about the testing process?
So it's actually an interesting problem figuring out how to test these payloads, which came from very diverse places with very diverse functions, and that were going to be potentially accommodated on a mission to the moon, on a lander that wasn't yet selected, and on a host spacecraft mission that also wasn't selected. So to do this, we took kind of a twofold approach. The first, we looked at just characterizing whether they would survive during launch events. So we did random vibration testing using standard NASA specification for this. We took all 3 payloads, put them on a vibration table, shook them, see if they turned on afterwards. Everything so far so good. The other aspect was thermal vacuum testing, and that's did we think that we could survive in the lunar environment. This, we took a more custom approach. The standard NASA spec wasn't quite designed for this mission where it could be a single cycle on the lunar surface. So we took a pretty simplistic test approach of 1 cycle from minimum temperature to maximum non-operational temperature, and then 1 cycle from minimum temperature up to operational temperature, turning on every 15 or 20 degrees Celsius or so, see if these payloads are able to turn on, how they function, and inform the future if they move to a lunar mission and were accommodated. Did we think that they'd be able to survive and operate?
Now, these payloads were smaller than most payloads that would fly. Did that impact the testing at all?
These payloads were small. We actually originally set them at about half U, which is standard CubeSat size, about half of that. So it's about 10 centimeters, 10 centimeters, 5 centimeters. That they were so small, actually, the truth be told, made testing a little bit easier. We didn't need particularly large, complex tooling to be able to accommodate them. So it's actually made the testing go fairly smoothly, and it was pretty convenient.
What is the next step for these 3 payloads?
Yeah, so testing through vibration testing appears to be successful. Thermal vacuum is actually, as we speak, almost completed, and so far so good. If any of these are selected to actually fly to the moon, we'll begin the official accommodation process with our host missions. There'll be some interface, I'm sure interface hardware will be designed to manage them. They'll get delivered to those missions, and they'll get tested and certified along with those missions, and hopefully they'll get a ride in the next couple of years.
Sounds great. Josh Ravage, thanks for joining us on NASA Edge today.
Thank you so much.
It's interesting that these payloads from these teams were tested at JPL just like any other flight hardware or satellite would be for a mission. The vibration testing, the thermal vacuum, all of that. So these are legitimate flight hardware that could fly on any mission.
Yeah, that's what I love about what HeroX has done here. And in addition to a catchy title that led to a cool part of our show, as you said, Franklin, winners or just any of the teams that participated and got their hardware flight ready, they have a chance to fly to the moon. This is an incredible thing, and to have your hardware there is great. Now, I have some good news.
Okay.
There has been an announcement for a winner
really?
for the challenge. So all the teams did a great job. The 3 finalists were spectacular, but we do have a winner. It is Phil Jobson of Sunslicer.
The miniature X-ray spectrometer.
Yeah, with that cool dust mitigation gear mechanism.
Oh, very
really cool stuff. Yeah, they won. I sent him a message, and he sent us his thoughts on winning this challenge. Let's check it out.
Thanks for the kind words, Blair. Team Sunslicer is thrilled to rank first place in the inaugural NASA Lunar Payload Challenge, especially in the company of 2 other exceptional teams in Puli Space and Microrad. We're excited, over the moon you might say, in the possibility that Sunslicer, created in a Santa Rosa garage, may fly and validate 18 months of extreme commitment and sacrifice. I cannot thank enough my teammates Garrett Jernigan, John Doty, Brian Silverman, Vadim Gerasimov, and the countless volunteers, partner and sponsor companies for their tireless efforts. Please check out sunslicer.com for full credits and updates. And in the words of Ralph Cramden, to the moon, Alice.
I tell you what, Phil and his team did a really good job with Sunslicer. I mean, I'm looking forward to seeing that on the lunar surface one day.
Man, I can't imagine entering a contest like this and actually winning, knowing that, as you said, your technology, your creation might one day fly to the moon.
Yeah, we talked about this before with CubeSats. Can you imagine your resume at that point? You go like, I've done X, Y, and Z, but I also have a payload that's working on the moon. That's really cool.
And in addition to Sunslicer, we can't forget about the other teams that were in the competition.
Absolutely. And so when we were talking to the teams, we were talking to Tibor in Hungary, his whole team, which wasn't just there. They had team members in CERN, they had team members all over the place. The effort that went into this, and Christian, who was up at MIT, and his team, lots of hours, lots of creativity and innovation came together. And the good news, guys, and this is really important, that whether you win the competition or not, because of that testing that they've all gone through, each one of these payloads is flight ready and has the potential to fly to the moon. Good job, HeroX. Good job, game-changing in NASA. It looks like we got a winning plan for the return to the moon with Artemis.
You're watching NASA Edge.
An inside and outside look at all things NASA.
With show-ready technology.
I found a flaw in your system.
Uh-oh.
It's not the scale, Franklin.
Yeah.
You notice that?
You're like taller than everybody.
Hold on a second.
Oh, okay.
What do you think? Something like that?
That's
yeah, that's more like it. Yeah,
it's more like it.
Yeah.